Okay, so for our project, the first material we studied was a ceramic. For our specific material, we used a porcelain mug, as shown in the image here on the screen. There's a lot of different structures for ceramics, including linear, triangular, tetrahedral, octahedral, cubic, and I think that's it. Yep. As you can see, they're all shown over there in that chart, which is used to determine the structure based on the radii ratio of cation to anion. And then the mechanical properties of ceramics are usually fairly good. It's known to be a very strong material, but as shown here in the stress strain curve, the failure of a ceramic is very brittle, and there's usually no deformation. Alright, so here we're going to demonstrate the mechanical properties of a ceramic material using a mug, using a highly scientific strength test here. As you'll see, the fracture of a ceramic material is pretty brittle, which we'll demonstrate using the molecular structure here in a second.
I threw it on the ground. You must think I'm a joke. I ain't gonna be part of your system, man. Pump that garbage in another man's veins.
So here, seeing the molecular structure of a ceramic, there's very few slip planes, which cause the fracture of ceramic materials to be very brittle. Whereas like with metals, there's sometimes up to 12 slip planes. With ceramics, there's usually only 2 or 3.
All right, the next material we're doing is metals, and this is the stress strain graph for a ductile metal. I'll break down this graph for you. This is the elastic region. This is where any deformation or anything done to the object will go back to normal, like it can be undone. This is the yield point, and this is where we enter the plastic deformation region, and this is where any deformation or damage done to the object cannot be undone. It's more permanent damage. And the end of the graph over here is the ultimate stress, or the fracture point, and that's where the metal would fail and break completely. And in our demonstration that you'll see next, we don't actually get to the fracture point because the amount of force we would have to apply, we cannot achieve. So we'll probably get somewhere in the middle, get some major plastic deformation.
I'm here to demonstrate the properties of different metals. These are both aluminum, but they will undergo different deformations. This is a ductile fork, as you're about to see. We're going to bend this. And as you can see, this is a plastic deformation. This is not very undoable. And with the knife, you can see, putting the same amount of force, does not bend at all, actually. If you put enough force, I'm sure it would just snap. It seems more like a brittle metal. And to demonstrate that molecularly, you have a cube-shaped molecular structure here, but metals have slip planes. So as you add force and stress to it, it'll slip off like that, and you get dislocations and deformation.
The third material we did is polymers. There's 4 different types of polymers. We have linear, branched, cross-linked, and networked. And as you go from linear to networked, they increase in strength. There are 3 types of polymers. We have thermoplastic, we have elastomers, and we have thermoset. The one we're going to focus on today is an elastomer, and we're going to specifically use a rubber band. They're known for being extremely ductile and can stretch up to 1,000 times their normal length. Here's a stress strain curve for all 3 types of polymers, actually. We have the brittle ones, semi-crystalline polymers, and here is the elastomers we're going to focus on. As you can see, it's extremely ductile, and it's all elastic deformation. There's almost no plastic deformation until it breaks. And over here you can see this is the structure of what a rubber band would look like. As you can see, there are cross links. This is unstretched and this is stretched. And as you can see, when you stretch it, the cross links start to pull out, and that's what allows for the actual deformation and ductileness of the material.
So the next material we're going to move on to is polymers. Today specifically we're going to be talking about a thermoset elastomer. And so for first a macroscopic demonstration. Notice that the material can deform up to 1,000 times its original shape without breaking, until it finally breaks when the intermolecular bonds are broken. Now on a microscopic scale, what you're seeing is that this is our polymer. And so we have 2 chains of the molecules. Notice how they're also not the same size. And when when it's stretched, they deform and they come apart, but then they ultimately come back together. Now, what happens when they break is the bonds between the molecules break, and then that's when like a microscopic deformation occurs.
Oh
Oh my gosh.
Okay.
All right.